Hello all, myself Sambasiva Rao, working as Assistant Professor in the Department of Civil Engineering at VNR VJEC. I welcome you all to the lecture series on payment materials. The topic of discussion for today will be shape test and aggregate. So if you look at the importance of the shape test, so this is one of the tests that need to be conducted on aggregate prior to any strength test. So we are going to conduct different tests on aggregate in terms of strength, like aggregate crushing value, aggregate impact value, abrasion value, attrition value, or like that. So but before that you have to conduct this shape test, which is very important because it is going to tell something about the aggregate shape. The shape test is determine whether the aggregate particles are flaky, elongated or angular. So how they appear, whether they are leaf-like structures like flaky particles, which are called as flaky particles, or whether they are long elongated particles, which are nothing but elongation, which is having longest dimension. At the same time, the aggregate particles are angular, or whether they are spherical. They are going to give some information regarding the shape of the aggregate. So this information is going to help us in assessing the strength of that aggregates. So because these are going to affect these different kinds of aggregate particles, what we have over here is going to affect the interlocking property and stability when they are being used in the preparation of the mixes, either in terms of asphalt concrete or cement concrete. They are going to play an important role during interlocking, and they are also going to provide stability for the structure whatever we are going to construct. Flaky and elongated particles, these are nothing but leaf-like structures, and elongated aggregate particles break easily under load, reducing the payment strength. So these flaky and elongated particles, these are going to serve, these are going to form as weak points during the load transfer. So they are going to form as a joint, and they result in reducing the strength of the payment. So proper shaped aggregates provide better compaction and load transfer. So that is why we are going to look into the proper shaped size of the aggregate, not flaky and elongated particles. Of course, there can be some minimal amount of flaky and elongated particles there, but there is a limitation for which we have to consider them or not. Then only we are going to allow that aggregates for further testing. Aggregate particles, particularly, they are going to improve skid resistance and surface safety, but whereas the rounded aggregate particles or spherical particles, they are going to increase the workability. So if your workability is the main concern, then you are going to use the rounded aggregate particles, or if your interlocking is your main criteria, then you are going to use angular particles. So if you look into this, there is an index for measuring. There are three indices which have been mentioned to estimate the shape test. One is nothing but flakiness index. So this is a parameter which is used to tell about the contribution or the percentage of the flaky particles or thin particles or less dimension particles which are present in the aggregate sample what we have taken. Similarly, we have elongation index, which are going to tell about the long length particles, which are nothing but in one dimension they are in a longer length. So that is being told by elongation index. Similarly, we have angularity number test. This is going to discuss about the angularity or degree of sharpness or sphericality. You can tell that what is sphericity of the aggregate particles. Next, so size range. So here I have got some aggregate particles over here. So there are some 3 aggregate particles which are present over here. So this is one aggregate particle over here, and there is another aggregate particle over here. So there is another aggregate particle over here. So if I take this aggregate particle, if you look into this aggregate particle is going to have different dimensions. So along this plane it is going to have some dimension. Along this plane it is going to have some dimension. Along this other plane it is going to have different dimension. So this aggregate particle is not a single dimension particle until unless it is a spherical particle which is going to have a same dimension, that is nothing but exact diameter in all the dimensions. But whereas the aggregate particles what we are going to use in the construction are generally not a spherical aggregate particles. So because of which we cannot tell this dimension of this aggregate particle or an individual aggregate particle, we will not be able to tell the size of this aggregate particle. So for which we are going to prefer one term which is nothing but the range of size of the aggregate particle. I repeat, so you will not be able to tell the single aggregate particle dimension because it is going to have different dimensions or different directions. So because of which you will not confine to a single dimension. So that is why you are going to prefer sieve sizes. So you have to take the aggregate particles or the bulk of the sample what you are getting over there, and you have to put onto the top of the sieve. Okay, and you have seen there is a 10 mm sieve, there is a followed by 5 mm sieve, 2.36 mm sieve, and the top of the sieve appears like this with the square openings. So this is 25 mm sieve and this is 20 mm sieve. So you have to put the aggregate particles on the top of the sieve, and these aggregate particles will be passing through some 25 mm sieve, and some of the aggregate particles are retained on 20 mm sieve. So those aggregate particles are said to be of the size range 25 to 20 mm. Very, very important, because we are not telling the aggregate particle dimension for a single piece. So we are going to prefer the entire aggregate particles which are present from 25 mm sieve passing through 25 mm sieve and retained on 20 mm sieve. So that is nothing but this is the aggregate particle of size range 25 to 20 mm. So that is how you are supposed to tell the size of the aggregate particle. So now here I have one sieve with me which I have got over here for demo purpose. So this is one sieve over here. Okay, so this is 25 mm sieve. Okay, so basically if an aggregate particle is passing through 25 mm sieve, okay, it doesn't mean that that aggregate particle each and every direction dimension is less than 25 mm. It is not the case. So if I take this aggregate particle along this length, it is almost 15 centimeters. But if the aggregate particle is passed like this, it is passed along this shorter dimension, it is going to pass through the 25 mm sieve or 25 mm square opening. So this aggregate particle, if it is retained on the next sieve, which is nothing but 20 mm sieve, then this particle is termed as or designated as 25 to 20 mm sieve. But if you look into the other dimension, the longest dimension, it is much more higher than that of 20 mm sieve. So the note point what you have to remember, that is nothing but if an aggregate particle is passing through some mm sieve and it is retained on the next sieve, it doesn't mean that every direction dimension is less than that top sieve. That is nothing but every direction dimension is less than 25 mm. So in this case, this is longest dimension is higher, but if this aggregate particle have fallen like this, okay, then this aggregate particle have retained on 25 mm sieve. But because this aggregate particle have passed through this like this 25 mm sieve, then this is coming through the 25 mm, then we are going to designate it as 25 to 20. Similarly, I have another this key over here. So this also I am allowing it to pass through the 25 mm sieve, and it is able to pass through the 25 mm sieve. Then this also will be treated as an aggregate particle which is passing through 25 mm, and of course if it retained on 20 mm sieve, then this is also designated as 25 to 20. Similarly, I have one more aggregate particle like this. So I am taking something like this, so which is a flaky, both flaky and elongated particle. So if I'm passing through this over here, again this is going to pass through the 25 mm sieve, and maybe it might retain on the 20 mm sieve. Let us assume that all these three aggregate particles what I have shown over here, either a marker or a short scale and a key with me here. So all of these aggregate particles are passing through 25 mm sieve, and let us assume that they have retained on 20 mm sieve. Now we are designating all these three aggregate particles for the size range of 25 to 20 mm. But we also have to put a check. We also have to put a check that this is the sieve which is on the upper side of the sieve, and this is on the lower side of the sieve. We have to put a check to what extent can the aggregate particle can have the least dimension. So we have to put a limiting, or we have to put a permissible value. Even though the aggregate particle is passing through 25 mm sieve and it is retained on 20 mm sieve, the shortest dimension or the thickness of any aggregate particle should not be less than some particular value. So this is eliminated over here. So we are limiting that shortest dimension is only permissible up to this range. Similarly, we are also going to fix the longest dimension. That is nothing but we are also, even though the aggregate particle has passed through 25 mm sieve, one dimension can be higher than that of 25 mm. So we are also have to put the check for the upper limit. So that is nothing but we are designating this upper limit. So this is upper limit, this is lower limit. So beyond that we are not encouraging the aggregate particles which are less than this, and similarly we are not also encouraging the aggregate particles which are more than this. So that is the main purpose of the shape test what we are discussing today. Okay, now we define the what is meant by flakiness index. So flakiness index is the percentage by weight of the aggregate particle whose least dimension, that is nothing but thickness, is less than 0.6 times of the mean. That is very, very important over here. So you have to define the range or the extent up to which you can consider. So what they are telling is you have the flakiness index which is nothing but whose least dimension is less than 0.6 times of the mean. So just before we have seen that an aggregate particle is passing through 25 mm sieve and it is retained on 20 mm sieve. The mean of that is nothing but 25 plus 20, that is nothing but 45 by 2, that is nothing but 22.5. So this is your mean. Okay, so generally, if then spherical particles, we assume that all the aggregate particles should be of 22.5. If not 22.5, they will be ranging from 25 to 20. But whereas 22.5 is the mean size. But now we are going to set the tolerance limits for the lower value and for the upper value. So we have to go less than this. So on the bottom side, we have to go to the less than this value, 20 mm value, and on the higher side, we have to go to the higher than that of 25 mm. So we are going to see upper and lower limits. So the lower limit is nothing but it is defined as 0.6 times of mean. So that is nothing but your mean value is nothing but 22.5 multiplied by 0.6. 22.5 multiplied by 0.6. That is nothing but we are deviating by 0.4 mean. We are deviating from the mean 0.4, which is nothing but we end up with 0.6 times of mean. So that is nothing but it will be somewhere around 13.5 mm. So now, even though the aggregate particle range is 25 to 20 mm, we have set the lower limit, so it can have the shortest dimension up to this particular value, 13.5. Okay. Similarly, we are also going to see the longest dimension in the next slide. So this is this aggregate particle whose shortest dimension is less than 0.6 times of the mean. It means nothing but the aggregate particle which has passed through 20 mm and retained on 20 mm, we have to pass through the thickness gauge. Okay. Now here I am going to show the thickness gauge which is available with me over here. So that is what you can see over here. So like this. So for each and every size range, you are going to have this thickness slots. So these are said to be the this is said to be the thickness gauge. Okay. And this is nothing but these are individual slots which are available over here. Okay. So now you can see that there is a opening for 25 to 20 mm. So this is the opening which is provided over here. So this is being demarcated as 25 to 20 mm. Now I have taken the aggregate particles which are passing through 25 mm and retained on 20 mm. So and that mean value is nothing but 22.5 and 0.6 times of the mean is nothing but 13.5 mm. If you measure with some many scale over here, so this particular value 25 to 20 mm. So if we can check over here, it is exactly equivalent to 13.5 mm. So that is how this has been designed. Okay, so this thickness gauge has been designed in such a way that each and every size, so this is the size range of 63 to 50 mm. So you are going to take the mean of that and you are going to multiply with 0.6 times. Okay, then you are providing that slot over here. Similarly, for the next gauge, it is nothing but 50 to 40. You take the mean 50 plus 40 by 2, that is nothing but 90 by 2 multiplied by 45. The mean value is 45, and therefore you multiply with 0.6. So this will be 27 mm. So like that, so each and every slot has been provided in order to decide what is a flaky particle for each and every size range. So you have to understand that flaky particle is going to depend upon each of the size range and it is not unique for each for all the size ranges. So now I have got these aggregate particles also. Previously I have checked that these aggregate particles are passing through 25 mm sieve and they are retained at 20 mm sieve. Now one such aggregate particle is this which has passed through 25 mm and retained on 20 mm. I have checked this before coming over here. So now if I am passing through this over here along the shortest dimension, because we are very much interested in finding the thickness of this aggregate particle. So if I am passing over here, if this aggregate particle least dimension, that is nothing but thickness, is less than 0.6 times from the mean, this aggregate particle is going to pass through this slot. And then this aggregate particle will be termed as flaky particle. Now this aggregate particle is not passing through this slot over here. So then this aggregate particle is not a flaky particle. This is of the size range. The thickness is more than 13.5. Now I have the another aggregate particle which is passing through again 25 mm sieve and retained on 20 mm sieve. Now I am passing along the thickness. So along the thickness, now I am passing through this aggregate particle, but this aggregate particle is passing through this slot provided over here. So in the size range of 25 to 20 mm, this aggregate particle, which is nothing but a leaf-like structure, so this aggregate particle is nothing but a flaky particle. Okay. Now similarly, I have also tested that this is one particle which is passing through 25 mm and retained on 20 mm in front of you. Now I am passing through this, again the same slot 25 to 20, it is easily passing through this. So we have designated the thickness slot for this size range is 13.5, but hardly the thickness of this is nothing but 2 mm. So this is very, very flaky particle. So we should not encourage the aggregate particles of this criteria in our construction. Similarly, there is another aggregate particle which is I have shown in front of you, which has passed through 25 mm sieve and retained on 20 mm sieve. Now if I am passing through this again, the size range of this, it is also passing through 25 mm and 20 mm sieve. Now this aggregate particle is nothing but flaky particle. Okay, now again, this is another one aggregate particle which I have shown in front of you, passing through 25 mm. Now I'm passing through the thickness slot of 25 to 20 mm. It is not passing through this thickness range. So it means nothing but this is not a flaky particle for the size range 25 to 20 mm. So this is very, very important. I hope this is clear. So you are designing, even though the size range of the aggregate is 25 to 20 mm, you are setting the lower limits. So regarding to flakiness index, it is nothing but we are going to set the lower limits, and the lower limit value is nothing but 13.5 in terms of the 25 and 20 mm sieve. So I have given the slot over here. So this is nothing but 25 mm and 20 mm. So this is nothing but 0.6 times of the mean, that is nothing but 13.5 mm. So as the mean is 22.5 multiplied by 0.6, so that is 13.5. Similarly, you can verify each and every slots are going to be 0.6 times of their size ranges. So this is regarding the flakiness index. Now you have to take this test is being supposed to be conducted for the aggregate particles which are less than 63 mm, okay, and higher than 6.3 mm. So this is very, very important. You have to take the aggregate particles which are less than 63 mm and which are higher than 6.3. You have to put on the sieve ranges over here, which has been mentioned over here. So the 63 mm sieve followed by 50, followed by 40, followed by 25, like that. And you have to get the aggregate particles which is being retained on each and every sieve. Once you get this, so these are the different values which have been thickness values. So for 6350 it is 33, and for just now what we have discussed over here, 25 to 20, it is nothing but 13.5. So this is nothing but 13.5 over here. So now you get the weight of that the minimum number of samples what you are supposed to get in each and every size range is nothing but 200 aggregate particles. There is no fixed weight over here. So for each and every size range, for 63 to 50, you have to get minimum 200 aggregate particles followed by 200 aggregate particles. Like that, you have to go when you are deciding the test, and when you are going to produce the results, you have to test for minimum 200 particles for each and every size range. Now let us assume that I have got somewhere around 5000 to 40 grams. For this aggregate particles, the weight of 200 aggregate particles which are passing through 63 mm and retained on 50 mm. Now then you have to pass through this aggregate particles along this thickness slot. So that is what been over here. For 63 to 50 is nothing but you have to pass through this slot, and you count the number of aggregate particles which are passing through this. Okay, because the definition is nothing but is the percentage by weight of the particles. First percentage we will look into later. So by weight of the particles whose least dimension is less than 0.6 times of the mean. If the least dimension is less only, then only the aggregate particle is going to pass through this. So it means nothing but you don't remember whether it is passing or retained, you look into the definition. It is telling that by weight of the particles whose least dimension, that is nothing but along thickness, is less than, if it is less than through this particular value, it is going to pass through this slot. So that is how you treat or you keep the flaky particles separately. And let us assume that somewhere around 10 or 20 particles have turned out to be flaky. So then the weight of that aggregate particles, so weight of flaky particles. So weight of flaky particles, let us assume that I have got 10. I am least bothered about number over here. So I am very much interested in weight, somewhere around 100. Okay, then your flaky percentage index, or that is nothing but flakiness index, is equal to percentage weight, that is nothing but percentage weight of the particles whose least dimension, that is nothing but which are passing through over here. So 100 divided by 5240, you will get the flakiness index value. This is only for single size range. This is only the single size range. Similarly, you have to conduct this test for all the size ranges over here. So you have to take the 200 aggregate particles for each of the size range over here. Okay, like that, and you mention what is the weight of the aggregate particles which is passing through over here, capital W1, capital W2, capital W3, capital W4. And let us assume that the weight of the flaky particles. So this is nothing but weight of flaky particles for each and every respective slots. So let this be small w1, let this be small w2, let this be small w3. Now you have to express the flakiness index for the entire range of aggregate, not for a single size range. You have to express for the bulk of the aggregate. So that will be equivalent to, your formula will be summation of, that is nothing but sigma of small wn. So that is nothing but you have to take the flaky particles of the size range 63 to 50 followed by 50 to 40, like that. So that is nothing but small w1 plus small w2 plus small w3 and so on, divided by capital W, that is nothing but sigma of capital Wn. So that is nothing but the weight of the original 200 particles you have taken for each of the size range, and then the overall value you can represent it as to be flakiness index. So I hope this is clear. Very, very important test that you are supposed to conduct in your laboratory when going for using the aggregates in your construction. So next slide. If we look into that, next index or parameter which is going to be here. So elongation index, the same more or less. The elongation index is percentage weight of the particles whose longest dimension, that is nothing but length, is greater than 1.8 times of the mean. Previously we have looked at, because we have set the lower limit. For example, we have taken 25 mm sieve and 20 mm sieve. So we have taken the mean value as 22.5 and we have went to a lower limit and we have set that to be 13.5. Now we are going higher than that of 25 mm. And we are setting the upper limit. So for which it is nothing but 40.5. So you can see over here, the same thing has been mentioned over here. 40.5 is the length gauge. So the length gauge has been provided over here. So this is the length gauge over here. So for conducting the elongation index, I have also got the elongation index over here, the length gauge with me. So this is the length gauge over here. So again the same thing. You have the size range for the 50 to 40, followed by 40, 30, 31.5, 25 to 20. Now I'll just explain the aggregate particles which I have taken previously. So this is an aggregate particle which is flaky, which we have tested in the previous thickness gauge, and it has passed through the thickness gauge of 25 mm to 20. It means nothing but this is treated as an flaky particle. Now we want to check whether this aggregate particle will also be an elongated particle or not. So when I am passing through 25 mm 20, it is passing through this over here. Okay, it is passing through over here. But by definition, whether it should be passing or it should be retained means whose greatest dimension is greater than 1.8. Greater than 1.8. So if this aggregate particle dimension, longest dimension is greater than 1.8, it should be retained. It should be retained. So now if your aggregate particle is retained over here, then that will be treated as elongated particle. Or else if it is easily passing through over here, so then this is not an elongated particle. This is basically a flaky particle only, but not an elongated particle. And I have another aggregate particle similarly. So I am passing through 25 mm 20 mm sieve, and this is not an elongated particle. Why? Because the longest dimension, that is nothing but along length. When I am passing through this aggregate particle along length like this, okay, so this is not being retained over here. It is not higher than this how much? 40.5. It is not higher than 40.5 mm. So it is not going to retain over here. If it is not retained, it won't be an elongated particle. Similarly, the third aggregate particle, of course it is very angular, so it will not be definitely an elongated particle. So but previously I have shown another 3 kind of aggregate particles like this. So we have treated this an aggregate particle. This aggregate particle is passing through 25 mm and retained on 20 mm, and we have checked this in terms of flaky particle, flaky thickness gauge. It has come out to be flaky aggregate. Now we are checking this in terms of the length gauge. It is 25 to 20 mm. So I am passing through over here. It is retained. Okay, it is almost 3 times more than that of the length slot provided over here. So this aggregate particle previously established as flaky particle. Now this aggregate particle has also been established as elongated particle. Previously it was flaky particle. Now it has proven as to be elongated particle. Now similarly, I have this aggregate particle which is not flaky. Previously when I passed through the thickness slot, it did not pass through there. When it has passed, then it is a flaky particle. When it is retained over here, it is an elongated particle. So it did not pass through the thickness gauge. So it is nothing but a non-flaky particle. But when I am passing through this 25 to 20 mm sieve, it is an elongated particle. So it is not a flaky particle but an elongated particle. But whereas the previous short scale what I have tested, it is both flaky and elongated particle. Now this aggregate particle which is also passing through 25 mm and retained and 20 mm sieve, it is passing through thickness slot. So that is why it has come up to be flaky particle in the previous discussion. Now I am passing through the length gauge. So this is nothing but 25 to 20 mm. It is retained over here. So this is the longest dimension is higher than that of 40.5 for this size range. You have to be very, very particular about the size range. You cannot bring this aggregate particle which is passing through 25 mm and retained on 20 mm. You cannot pass it over here, okay, and you tell that this is not an elongated particle. You have to test this aggregate particle in the respective length slots and in their respective thickness slots. So this aggregate particle has turned out to be flaky particle and elongated particle. So this is how the importance of, because these aggregate particles when being used in construction, either flaky and elongated particles, they are going to break easily, very easily. They are going to form the weak bonds and they are going to reduce the thickness. They are going to reduce the strength of these pavements. So we have to be very, very particular while calculating the flaky and elongated particles. Here also the same process being involved over here. So you have to take the minimum 200 sizes of the aggregate particles. So each of that, and you have to take the weight. So for example, here this will be, again, let it be capital W1, capital W2, capital W3, and so on like that. And let this be a weight retained on length gauge. Here, because the longest dimension is greater than 1.8 times of the mean, we have to take into consideration the aggregate particle which is retained over there. So similarly, we have to get the small w1, small w2, small w3, small w4, and so on, so forth like this. After that, your elongation index will be, the formula will be summation of all aggregate particles which is retained on their respective length gauges. So that is nothing but summation of small w1, small wn, which is nothing but w1 plus w2 plus and so on. At the same time, divided by summation of capital Wn. So that is nothing but the original weight of the 200 aggregate particles, whatever you have taken. So similarly, you can express this as elongation index. The limiting value being prescribed in the code is nothing but the elongation index value can be up to 15%. Okay, and but whereas the flakiness index also can be 15%. So this is how you conduct the flakiness index and elongation index. So this test what we have conducted so far is nothing but individually we have conducted a flaky test and we have conducted the elongation test separately. Now the third one is nothing but it is a combined flakiness and elongation index. So this is the table corresponding to combined flakiness and elongation index. So the size ranges are mentioned over here, 63 to 50, 50 to 40 and 40 to 25. So we have to take the capital weight. So that is nothing but total weight. So this is nothing but total weight over here. So this is nothing but capital W1, capital W2. This will be slightly different from what the test what we have conducted so far, individual flaky and elongated particles. Now here we have found out, we have passed through the thickness gauges and we have found out aggregate particles of each and every size range, whether each and every particle is an aggregate particle or not. Basically we have taken 200 aggregate particles over here, 200 aggregate particles over here, and we have taken, measured their weights and represented over here. After that, we have conducted the flakiness test and we have expressed the weight of flaky particles. Weight of flaky particles is nothing but the particles whose shortest dimension is less than 0.6 times of the mean or which are passing through their respective thickness slots. Now, the weight of that particles which are passing through each and every slots are nothing but W1, W2, W3, W4 and so on. Now, here very important, weight of non-flaky particles. This we didn't discuss so far. Here it is non-flaky particles. This is just a reminder over here. So once you conducted flaky test, you have to remove the flaky particles over there. Or else previously we have discussed the flaky test separately and we merge all again together. We will take the same 200 particles and we'll do the elongation test. Okay, some particles which are flaky and you again measure into that again 200 particles. You are doing the test later on, elongated particles. So some particles will be elongated particles. Now, when you are referring to this combined flakiness and elongation index, you have to follow a caution that you have to do a combination of elongation and flaky test. Okay, it means nothing but you have to do the first flaky test and you separate the weight of non-flaky particles. Okay, for example, I have taken some 5000 grams over here and let it be 200 grams be flaky particles. So then the remaining weight is nothing but 4800 is your non-flaky portion or non-flaky particles. That is very important, because if you are allowing the flaky particles inside and you are conducting the elongation test, even though the aggregate particle has turned out to be non-elongated, but it is previously a flaky particle and you are unknowingly allowing into your aggregate. So for which we have to put the restriction for the flaky particles which have been turned out to be flaky when previously we have conducted the flakiness index. So that is how you have to take the, let this weight be Z1, which is nothing but this Z1 will be, Z is equal to, I am writing over here, Z is equal to capital W minus small w, capital W1 minus small w1. So this is small w1. So it means nothing but weight of the non-flaky particles. Now you have to take this non-flaky particles and you are supposed to conduct the elongation test. Now again the weight of elongated particles. Weight of elongated particles. So far we have taken weight of 200 particles and then weight of the flaky particles and weight of the original 200 particles minus weight of the flaky particles. You have arrived at the weight of the non-flaky particles. On the particles which are non-flaky, you are supposed to conduct the elongation test and you will getting some elongated particles. Let the weight of that elongated particles in each and every sieve will be Y1, Y2, Y3, Y4 and so on. Let this be Z, Z2, Z3, Z4 and each and every respective sieve ranges. Z1, Z2, Z3 are non-flaky aggregate particles and each and every size range. Now you have weight of the elongated particles Y1, Y2, Y3, Y4 like that. Now you have to express flakiness index over here. Flakiness index is nothing but summation of small wn divided by capital Wn. That is nothing but W1 plus W2, small w2 plus small w3 and so on so forth divided by capital W1, capital W2 and so on so forth up to Wn. So then you will get the flakiness index. Okay, this is, you will be getting over here. So you have to take the summation. So this will be a single column like this. Okay, because you have taken small w1 divided by small w1 plus small w2 plus small w3 and so on divided by capital W1. So this is, will not be having so many rows over here. It is a single row. Okay. Next one, similarly, here elongation index is equal to summation of small yn. It is not something else. It is yn, which is nothing but elongated particle on size range 63 to 50 like that. So divided by capital Zn. So that is nothing but, in the denominator it is nothing but summation of non-flaky particles. I repeat, flakiness index is nothing but weight of the flaky particles divided by total weight of the 200 aggregate particles what you have taken in respect to size ranges. And after that you will be arriving at non-flaky portion, which is nothing but represented as Z1, Z2, Z3 and so on each and every respective size ranges. Then you are supposed to conduct the flakiness test, elongation test on non-flaky particles for each of the size range. And you will be ending up with y1, y2, y3 as the weight of the elongated particles in their respective size ranges. Now your elongation index will be summation of the elongated particles on each and every size range divided by summation of non-flaky particles on each and every size range. So that you will be getting again a single value over here. So let this be somewhere around some 16 like that and somewhere around 15 assumption. So then your combined flakiness and elongation will be here 31%. Our code recommendation is up to 35. So this is acceptable. So this test is very, very important. So far we have conducted flaky and elongated individually. So you can represent flakiness portion individually and you can represent elongation portion individually. But here it is a test where you have do the interconnected test and where you can remove flaky particles aside, such that that will not end up in next will not be considered for elongation test. So next one, the third parameter, the third index, which is nothing but angularity number. Angularity number is a numerical measure of how angular your aggregate particles are nothing but. Okay, so our sharp-edged aggregate particles, it is defined as very, very important, the percentage of air voids in excess to 33. Okay, so here I have two ways of arranging an aggregate particles, assuming that they are spherical in shape. So this is one kind of packing, which is nothing but cubical packing or square packing, where huge amount of air voids is been created or a huge air void ratio has been created. But whereas this is an hexagonal packing where the dense packing, this is also called as dense packing and this is also called as loose packing. If you have dense packing, you will have minimal void ratio. In aggregate, it will be taken as minimum will be 33% air voids. So how much ever you compact the spherical particles in a given cylinder, you cannot arrive void ratio which is less than 33%. So in the entire V volume, you are going to be having 33% air voids and remaining 67% will be solids volume. So Vs will be 67% of course. Okay, but whereas this is the loose packing, so we are not interested anyhow these values over here, so I'm not going to take that into discussion. Anyhow, I just wanted to show you that this is one kind of packing where you have the loose packing and will be having higher void ratio when compared to this. So any arrangement will be of this range, so you can have a minimal void ratio of this much. So you cannot compact less than this void ratio and you cannot compact similarly more than that. Okay, so now your aggregate particles are nothing but your angularity number is nothing but Va minus 33 percentage of air voids. So smallly, if I try to introduce replace this spherical particles with angular particles, now your percentage of air voids will be keep on increasing. Why? Because previously I have taken all of the particles to be spherical and this is nothing but hexagonal packing where it is a dense packing. So it has attained at the dense state where you have air voids to be 33%. Slowly, once I started introducing the angular particles, my air voids are going to be increased and it is going to be increased more than 33%. So more voids are going to be created when compared to the baseline, which is nothing but 33%. After that, after some introduction of this aggregate particles in the same container again, you have to compact, not too much compaction, you have to fill up to the brim of that jar what is being provided over here, provided in your laboratory. So then after that you have to measure the air voids. Okay, so once you get that air voids, so you have to separate. For example, my air voids are nothing but 44, then 44 minus 33. So air voids in excess to 33. So how much is in excess? So that is nothing but 11. If it is 40 minus 33, it will be 7. So this is how you estimate the angularity number. I repeat that angularity number is nothing but void ratio in excess to 33%, or you can tell that in this case void ratio is 33%, means solids volume is 67%. So you can also tell that solids volume indeficient to 67%. So that is nothing but solids volume indeficient to 67%. So 67 minus existing solids volume. So if it is less than this, so then we'll get somewhere around, how much is that? That is also an angularity number. For example, 67 minus. So upon introducing angular particles, my air voids has been increased. Therefore, my solids volume has got decreased from 67 to 60. So therefore, your angularity number is 7. So the limit for angularity number ranges from 0 to 11. So if your angularity number is crossing more than 11, then then that is an indication that there is higher contribution of flakiness and elongation index. So why? Because the introduction of flaky and elongated particles, because of their orientation, they're going to occupy more space, and they'll not lead to a dense compaction state. So because of which you are going to have higher amount of air voids. So because of which your angularity number will fall drastically. So this test can also be an important test before conducting flaky or elongated. So both are interconnected. So if you have an estimation of angularity number, you can just understand that based on that how much will be the approximate value of flaky and elongation indexes. So you don't have the direct formula because you cannot measure the air voids in the given cylinder whatever is being provided for doing this angularity test. So we generally measure with angularity number is equal to solids volume in excess to 67%. So this is angularity number. So there is a formula over here, 67 minus. So this is the weight of the aggregates. So in the cylinder, this generally there will be a cylinder like this. Okay, you have to fill this aggregate particles entirely to the brim, not too much compacted, just like that. So of course these aggregate particles are not spherical, so there can be anything. For simplicity I have represented like this. So weight of that aggregate particles filling this cylinder divided by weight of that water, and followed by specific gravity of that aggregate, then this will give rise to angularity number. But if it is an objective question, then they tell, if they ask like what is the angularity number when the air voids are 40%, then you can just subtract 33 from 40 and you can express it as 7. But whereas when you are asked to calculate in terms of solids volume, okay, you have to do in the laboratory by calculating solids volume. You cannot do by measuring air voids because it cannot be measured. So there is one small problem over here. The weight of the coarse aggregate having specific gravity, so the G is given, which is completely filled in a cylinder of volume 0.003 meter cube. So the volume is given, volume of the cylinder, it is nothing but 0.003 meter cube. As we all know that 1 meter cube is equal to 1000 liters. So the volume will be 3 liters. Meter cube is equal to 1000 liters. So you multiply this with 1000. So you'll end up with 3 liters. Of course, the water weight is nothing but 1 liter is equal to 1 kg. So therefore, you can take it as 3 kg. So weight of water will be 3 kg. Now your angularity number, the formula as discussed previously, it is 67 minus weight of that aggregate particles divided by weight of the water multiplied by specific gravity. So this is whole separated in a bracket. So 67 minus weight of that aggregate particle is nothing but 5247. Of course, this is in grams, and whereas we have the weight of water in kgs. So I'll express this also in terms of like this. So then you can calculate what is the value of this. So once after I don't know what is the value coming over here. So whatever it might be. So for assumption purpose, let it be 60. So therefore, your angularity number is 7. So this is the angularity number. So this is the basic discussion regarding the shape test. One is nothing but flakiness index, followed by elongation index and angularity number. So I sincerely acknowledge the use of publicly available resources that supported and enhanced the visual clarity of this presentation. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.